first announcement about meeting number 2. We are going to have that this Thursday, April 2nd. Okay, I will post the questions at 5 p.m. Hopefully, should be able to do that. Okay, and then most importantly, it's going to be due at Tuesday next week, and then it's like submission homework. You do need to make it before 12:30 to upload your file. Okay, I prefer PDF. It's easier for me. I can just put your scores on and then send it back to you. Okay, but if you are saying you always do like Word file, it's okay. I possibly will convert your Word file to PDF as well. I will try that way, but I don't know it will be successful to reserve every character you have for Word document though. So any question on the meeting number 2? Okay, I assume you guys are ready then. Okay, let me see. Anyone have any questions? No? Okay, so just this morning, I learned about the so-called room bombing, which means that somebody is going to randomly go to the room and then trying to destroy things. I'm kind of surprised on that. Anyway, so far so good in our class. So the school actually the things trying to keep you guys in some way to make sure that everyone in this room meeting is eligible. So since so far I don't see any troublesome happens in this room meeting in my class. So let's not do that first, but really in case any really bad thing happens, then we will do some kind of waiting rooms for everyone to come in, okay? Because I see there's a bunch of work to assign everyone coming to the regular classroom. It's good. Okay, so I do want to make some comments before the class. It's really also related to your meeting number 2 as well. Okay, but hopefully it's not confusing though. Let me see what that is. Why I say it's hopefully it's not confusing. Okay, so I said in class when we doing the LRT, then I'm saying that you need to find rejection rule, right here. Say you need to find a rejection region. Basically, I have the data, and then the rule would be it's lambda x more than c. This is my rejection rule. Okay, and I say most likely you don't know about distribution of this guy lambda x right here. So I want you to find equivalent region. Right? Likely is what? You find out easy statistic Tx. This more likely is MLE, more likely. I would say you need to draw a graph bigger than C1 star or Tx smaller than C2 star. One of that. So either or one of it. Okay? You need to talk about it. Looking at the graph, you need to find a direction of the Tx's. And I say it's most likely follow the direction of your alternative hypothesis. Okay. So actually, at some case, for example, this one right here. Let me see. This one right here. If you do have, I'm talking about this one right here. Okay. If you do a lambda, this is projective function. Okay, this projective function. And then, maybe this may be too small. Let me draw on the side, on the side. Okay. differential right here is bigger one. Okay. So I said this is quadratic function right here. Okay. And then this is some kind of lambda x. And then this is what x bar, I think. Okay. I this is quadratic function. Ever is, hold on, sorry, messy right here. What we are looking for is what? This is C, right? And then lambda x somewhere in C. This is my rejection region. And then I say right here, okay? Lambda is possibly too complicated. You need to find what? This is two regions as equivalent. So C1 star here, and then C2 star here. And then this is my rejection region as R. Equivalently, you find this region, the null hypothesis. Okay? Then eventually, you're using alpha equals to probability of x bar bigger than C1 star or x bar smaller than C2 star to find it. And I say you can divide it by half, right? And then to find C1 star and then C2 star. Okay, good. So if it's for you, you can go for it. Okay, trying to draw a graph and then to find quadratic function to find the equivalent regions. Okay, however, is there, as you can see, what lambda x is, especially you do have something right here. Okay, so that means I can also using lambda x smaller than c, then do some transformation and to give me that equivalent region, for example. Okay, right here I think this is null space is 1 point, so that means lambda x is exponential, then minus and then x bar minus theta 0 square, then divided by 2. Okay, divided by 2 is outside, right? So that means this guy divided by 2 right here, smaller than c. Okay, so through that easy algebra operating, for example, taking log on both sides, right hand side, for example, it's okay, just be careful about everything right here, divided by 2. Okay, taking log, don't have to change sides because log is monotone increasing function. You don't have to change size. But whenever you do on negative, you do need to change size. Change the sign of the equation of inequalities. I should say that bigger than 2 times log c divided by n. Okay, and then of course you can also delete it, like I have right here. Right? I can say I can take out the square. No, it's not right. I can taking out square, but keep in mind is this guy got to be bigger because you got to put also very right here because you don't know that's positive or negative. You could do this as well. 2 log c divided by n. The same thing I have right here is minus, of course, minus, and then okay. So think about it. If you can say, well, my right hand side right here is a C star, for example, if I can say so, right? Everything is constant, so I can say C star. So this guy right here is nothing but what? I can say X bar, right? It's wrong. I don't like it. So I should be say so it because this guy's bigger. This guy is bigger right here, right? Your absolute value bigger than C star, which means that it's your x bar minus 0 bigger than C star, or your x bar minus 0 smaller than minus C star. Right here. It's actually getting back to what? Getting back to right here. Okay? Which means that it's, if you can draw a graph, then looking for these equivalent regions, go for it. Sometimes you may also just doing that algebra right here, right? Algebra to find eventually your x bar bigger than C1 star or x bar smaller than C2 star. Right here is what they're actually having some kind of connection right here. Okay, so sorry about that. So this x bar smaller than C2 star right here. Then writing this is actually going back to this and this. Okay, I find some chat. Okay, good. Okay, again, so I'm not saying everyone could everything. I'm not saying every LRT could do that. As you can see, the meter number 2 in the past year. I don't think you can do that right here. But also, it's the same thing if we look at next example right here. Okay, right here. It's about like the exponential case. Okay, you can actually do that as well, I think. But it maybe needs some kind of operation because you do have more complicated lambda x right here. But eventually you can move everything by that operation. You can move everything to the right hand side like that. Okay, if we can do that, do it really easy operation on the move here and there. Eventually you can write down, for example, right here. It's right here. If your rejection region right here is what, if eventually if you alpha again, probability of your x1 bigger than, if you can do that easy operation right here. Okay, so that means you could just using this guy to find where the right hand side is. Just name that C1 star, C star things. C star things right here. Okay, using that to find what C star is. Of course, if you remember that this is more complicated because you were, okay, this guy is, null space is what? Null space is theta, smaller than theta 0. Okay, so remember that you do need to find x1's PDF, and then the whole thing is 1 minus CDF, and then calculate the right hand side. Then you talk about the maximizer happen in the theta 0. Okay, right here. Okay, then using that to find C star. I think that's in the last note of I have. Okay, good. So which means that it's, you don't really have to draw your graph, lambda x, and then x1 right here, and then going down right here, and then you find smaller than C, actually bigger than x1 bigger than something. Well, this got easier, drawing graph easier. But if you cannot draw a graph, you might have a chance to do operations to get this guy right here and to find a cutoff. Okay, hopefully it's not confusing. Okay, hopefully you just do you can just using the graph and you can find the equivalent region. But if you can't, trying to do the operation, or you can double check it to see if both have the same rejection region then. Okay, good. Let's move to the next one is what? Move to the next one, it's power function. It's Okay, let me put it bigger. Okay, good. So last time we talked about how to be evaluate a test. Okay, so the way we do evaluation about testing is actually draw power curve. So power function definition beta theta. This guy is rejection region. The point is there is theta right here. Could be ranging from null space and alternative space. So that means even as power function, the theta actually cover two spaces, not just null space. Okay. Then we talk about two testing. One is size alpha test. Size alpha test means that this guy exactly equals to alpha. Okay, this one type 1 error, exactly equal to alpha. Then level alpha test would be what? Small or equal to alpha. Okay, that's the difference between size alpha test and then level alpha test. Okay, so right here is what? If x1 to xn, again, pay attention to which one you do know that already. This guy is known sigma squared. Okay, so this guy known, so you don't have to do any testing or estimation. Then you do testing. Your null hypothesis theta, so theta 0. The alternative is theta bigger than theta 0. Okay, so by so many things happening about LRT you've been doing already, I anticipate you would know how to find bigger than C. Also, I would anticipate you might find out this C actually equals to Z alpha, which basically is quantile. Let me make sure alpha, I think it's 1 minus alpha, I think. This normality bigger than C is alpha. This guy is alpha right here. I think this guy is Z1 minus alpha by my usual quantile notation. It's 1 minus alpha. Okay. Z1 minus alpha. It's okay. So this is a typical question I will give you in method number 2. Okay. Finding LRT's test region as well as finding what color of it. Okay, good. Then how if I know that there's a test, how do I find the power of a test then? Okay, so really just by definition, you write down your power function beta theta, and remember theta could be null space, LRT region like this guy right here. Theta not necessarily is a true theta. This is one thing you need to pay attention to. Okay, students are confused about why sometimes theta now, but sometimes it's theta. Okay, just keep asking yourself, what is a true theta? Right here, true theta right here, not necessarily in our space. It could be alternative space as well. Okay, good. So like that, then you just do operation, right? From here to here, from here to here. I mean, it's not really big one to do. Let me see if I can. Okay, for example, right here, it's I want to name it. Okay, so right here is what probability theta, then x bar one theta 0, then sigma squared divided by then bigger than C right here. Let me put smaller one and then put bigger one. Okay, so right here is equals to what? Remember again, true theta here. Because true theta is theta, so you basically move everything to right hand side plus C sigma squared divided by root n right here. Okay, and then your true theta is here. So that means in order to standardize, you minus theta, then divided by sigma squared divided by n. The reason you do that is this guy's actually follow normal 0, 1. Okay? Again, you have to really remember this guy, not necessary. I'm not saying it's not, but not necessarily follow normal 0, 1. Okay? The right guy follow normal 0, 1 is this guy. Okay? Then if you do that in the left-hand side, you do that in the right-hand side, which means that it's minus theta, then divided by right here. I can say z as a normal 0, 1, then bigger than what? This guy cancel out, then bigger than c, then plus, I think. I write plus or minus. I write plus. So theta 0 minus theta, then divided by square square divided by n. It's exactly what I have right here. Okay? Good. And then, so this is a power function. And the function is, this power function is function of theta. Function with theta right here. Okay? So then you do have this guy writing out. You do this guy follow normal 0, 1. Okay, normal 0, 1. Then this guy's bigger. So that means I can write 1 minus this is normal 0, 1 is CDF. Like this. Okay? So then to write power function, you do equals to this guy right here. It's a power function. Then for power function, okay, power function will look like this. You do have your power function. Okay, good. You do a power function beta theta. And then you do have a theta in the x-axis. Okay? And you're looking at this guy right here. Or maybe this guy right here, I can just say 1 minus phi, then c plus, okay, theta 0 minus theta, because I do the n right here. Sorry about that. I don't know what happened. Okay, I tried it more. Look at this. Okay, say right now, because I told you C is what? I told you C is Z1 minus alpha, I think. Okay, good. So power function look like this. You actually choosing theta equals to theta 0. Say this guy not then it's 0. I say this guy theta 0 first. Theta 0. Okay. If you putting down theta by theta 0, what happens? That means the probability theta 0. So I'm sorry. So should be beta theta. If I actually plug in beta with theta 0, this guy become what? Become 0. That means 1 phi z 1 minus alpha. What does that mean? That means this guy right here. Okay, this is z 1 minus alpha. That means this guy right here, it's 1 minus alpha. Sorry, wrong. This guy is alpha, right? Then this area is what? This area is 1 minus alpha. So that means this guy right here, normal 0, 1, accumulated until z 1 minus alpha is what? 1 minus alpha equals alpha then. Okay, so that means as long as you plug in theta, theta 0, this guy right here is alpha. Okay, then imagine that. Imagine what happens when you theta goes to infinity. Okay, so that means if I do have theta going to infinity, that means right here, this guy goes to infinity. This is the minus term right here. That means the whole thing right here is minus infinity. This guy constant, doesn't matter at all. That means whole thing will become minus infinity. Making sense? Okay. So if we replug in theta by infinity, then this guy right here become minus infinity. We do know that CDF of normal 0, 1 minus infinity is what? Is 0. So that means this guy is 1. So it means if I got theta goes to this way, okay, then this guy going to what? Going to infinity. Of course, this guy is increasing function of theta. We can talk about that later on. But just imagine if theta goes to larger and larger, then it eventually goes to infinity, then it goes to 1. Likewise, what happened to theta goes to minus infinity then. Okay, theta minus infinity. If you plug in right here, this guy, if I plug in minus infinity, what happened? Positive infinity. Whole thing become positive infinity and then plus constant. So eventually 1 minus v positive infinity is. Okay. Again, CDF, normality, positive infinity, this guy become 1. Eventually becomes 0. So imagine that is if it goes to left hand side of the theta, then you goes to close to 0. Then this is basically what the power function curve of this test is. Then how do I know it's increasing function? You're going to be paid to this. How do I set this increasing function then? Right? It's actually not hard to imagine, isn't it? So pretty much like I do have normal 0, 1 right here. Okay. So whenever I theta getting bigger, what does whole quantity getting it? Because negative term right here, right? Negative term right here. That means as long as something getting bigger, I do have negative right here. It's when theta getting bigger, your quantile actually move to the left. Could you imagine that? Okay. So whenever quantile moving to left, this guy is 1 minus phi is actually left-hand side probability. Do I mess up? No, right-hand side probability. Sorry about that. It's actually right-hand side probability. Okay, right-hand side probability. Okay, 1 minus phi is left-hand side probability, 1 minus the right-hand side probability. So because my quantile getting smaller, whoops, because my quantile getting smaller, my right-hand side probability getting what? Getting bigger. So then it's not hard to imagine the whole power function is an increasing function of theta. Okay, such that I can feel free to show that it's feel free to show it. This is increasing function of theta. Okay, so this is a typical what it looks like power function for one-sided test. Later on, if I have a chance, I will show you what is a power function of a two-sided function. It's two-sided test. It's. Any question on this? So after meter number 2, you guys will homework number 8, I think. Then in homework number 8, I will definitely give you something to draw a power function with. Okay. So at a time, you do need to know how to draw a power function as a function of theta. Okay, good. So if there's no questions, let me see. Okay, no question on check box. Okay, then I'm going to talk about so-called power function under binomial distribution. Okay, this is something you want to know a little bit about because we talk about power function right here is continuous case. X1 to xn is RID normality. Is continuous random variable. Right now is I can also do power function on discrete random variable. And you will see what I want to talk about it. Say if I only have a single x, okay, follow binomial n theta, n is three right here, n theta, 3 theta. And look at the primitive space. It's from 0 to 1. Okay. Any points between 0 to 1 could be my theta. Okay, good. And your null hypothesis what? If we say the smaller, so that means Joe bigger one, right? One right here. I have 1, 4, 3. Then this is my alternative space right here. Okay, one is smaller than 1/4, the other one is bigger than 1/4. Okay, then you can propose in a test. Say, indicator function x equals 3. What does that mean by this test? Which means that it's as long as I observe the observation is 3, I reject the null hypothesis. Okay, so because right. Okay, so one of them is what? As long as I observe 3, I reject it. Then what happens to if I observe 0, 1, then that don't reject. That's it. Okay. Good. And as long as you have one test, you can calculate what's the power of a test. Okay. So power test is what? Okay, this general power function is beta theta. Then given some general theta, it's then x equals 3. Okay. Because of x is binomial, that means n is 3, choosing 3, then theta 3, then 1 minus theta. Oh, sorry, 1 minus, a little bit right down, 1 minus theta. Then 3 minus 3 right here. Then this guy become 1. This guy become 1. Eventually is theta cubic right here. Okay. As long as you can write the binomials PDF, you know what is probability x equals 3 gets. Okay. Then of course you can calculate size, but the potential size is under null hypothesis of the power function. Okay. So right now it's you do have your null space. It's from 0 to 1/4. And then theta cubic is increasing function of theta. Okay, which means theta getting bigger, you got your power getting bigger. Okay, pretty typical. And then right here, because the supremum under null space, the largest one is what? Because increasing function, it's happen in the boundary. And to be honest, always have in a boundary in our level of statistics. But sometimes talking about like finding supremum, finding maximizer, if your theta parameter space do have a boundary, the supremum always occurs in boundary. Okay, good. So next time, if you really don't know how to talk about, hey, what's the supremum is, then well, just guess in boundary. I think 99% you'll be correct, I think. Okay. So that the maximize happens in the theta equals 1/4. So you plug in, right here, you plug in 1/4, then cubic become 1 divided by 64. This is the power, this is the size. okay, of the test, right? X equals to 3, because x equals to 3. Okay, but in the meantime, you could also propose another testing right here, right? Which means that it's, as long as I observe x bigger than equal to 2, if I observe 2 and 3, and then I'm going to reject in the null hypothesis, okay? Then you can do that power calculation, power function. You can write down power function, beta star. And then inside guy is test region. General theta, inside guy right here is your test region, or is your critical region. It's right. Critical region is what? X bigger than 2. That means as long as I observe 2 and 3. Here you can write down probability of X equals to 2 and probability of X equals to 3. Again, using PDF binomial, you can get this guy right here. This guy right here. Okay, so that means right here it's I can calculate the size of delta star X. Okay, again I could put supremum again theta in null space, then calculating the power function. Okay, again right here it's happen in the boundary. You plug in 1/4 the boundary of null hypothesis. It turns out to be 10 divided by 64. Okay, so which means that is, in some sense, as long as for all alpha bigger than alpha in this domain from 0 to 1, beta star all bigger than beta theta. What does that mean? That means you do have your delta x whose power beta star theta bigger than beta theta, which means that it's delta star is more powerful than delta. Okay, then it's not hard to imagine which one you actually prefer. Then you are going to prefer what? The test with more power. Good. So what I meant to say is that's intuitive, isn't it, right? So right here is imagine you are trying to reject the null hypothesis right here, right? This is null hypothesis we want to try to reject. And then theta in the smaller end of thetas from 0 to 1, which means is that if now actually true, you do wanna see 1, 2, 3 is a domain. You do wanna see you do wanna observe smaller value of the x-axis, which in some senses, as long as I observe smaller value, I would tend to think theta should be smaller value, such that you support null hypothesis. Okay? Which means that it's, as long as I observe bigger value, means what? I would tend to reject the null hypothesis of theta in a small value. It's making sense? So right now it's one. Okay? Then the other test, choosing both 2 and 3 or belongs to larger value of x. So that means that give you more options, give you more rejection criteria to say theta actually is a bigger value. It's okay. So it's not really surprising to me. Beta star going to be more powerful than beta because I do have more option to reject the null hypothesis. Okay, sounds good. Okay. So any question? If you don't ask question, you could just use chat box, or you could just raise your voice. Okay. Then next one would be it. Right now, look at again still the same binomial, 3 theta. But right now, my oval space only have 2 points, 1/4 and 3/4. And then null hypothesis would be theta equals to 1/4 versus theta equals to 3/4. Okay, good. Then under null hypothesis right here. Okay, again it's under null hypothesis. That means under null hypothesis, theta equals theta 0 equals to 1/4 right here. Of course, given that theta is 1/4, you can definitely using your binomial distributions to calculate the probability of equal to 0. Again, remember under null hypothesis. So under theta is 1/4 right here. Okay, so you can plug in to do calculation just right here. Okay, so let's do more general way again. It's right here. More general way equals to theta. That means you choosing 3, choosing x. True value is 1/4 x, then 1 minus theta, 1/4, then 3 minus x right here. Okay, so that means you plug in x0, plug in x0, plug in x0, plug in x0. You can calculate probability. It turns out to be 64. Okay. Again, you plug in x is 1, plug in x1 right here. Okay. Likewise, you can calculate probability x2, probability x is 3. You can get 4 probabilities. Okay. So imagine that you are doing testing, right? The data observe only single x. The data you can observe is just either 0 or 1 or 2 or 3, right? One of them. The only single observation. You are going to observe either one of them. 0, 1, 2, 3, 8. Okay. So if you do proposing your rejection region, really by what? You just by doing a combination things, right? This example is you could have a delta x equals indicator function x equals 3, right? That's one guy. You could also doing delta x is what? Indicator function x bigger than 2, right? The other guy. Maybe you can even doing what? Really lousy one, I think, is what? Indicator function of x more than 1. Any rejection region you can do it, but it's nothing but what? Combination of this guy, this guy, this guy, this guy. You can choose one of them, choose 2 of them, choose 3 of them. Really, your test region only you can do is combination of these 4 guys. Okay, so no matter what your lambda delta x is, okay, right here. No matter what you choose, right here, right? Eventually, the power or the size of the test is going to be what? Combination of this probability. If you are choosing 3, this guy right here, your power is this. Okay. If you are choosing this guy right here, it's a size. Your size is this. If you are choosing this guy right here, your size is this guy, then plus this guy. Okay. If you are choosing this guy right here, your size is what? This guy plus this guy. Okay. By the decision you choose. But there's really one critical point I want to mention. Size is actually a combination of probabilities. Do you have actual any testing could give you exactly equals to alpha as a think about it. The answer is no. By summation of these probabilities, right? I don't think you can find any combination. The size is exactly equals to alpha 5%. But sometimes that happens in the okay. Then if you do have this kind of thing, well, we are all talking about the type 1 error things, right? If your type 1 error not number one thing is I'm going to choosing a test. The size is going to smaller than 5%. Maybe by combination of these numbers right here, you might end up like saying it's 0. No. You might end up at, I should run this say something, 0.048. Okay, good. So if I do have a test by combination probabilities, the size is actually this. Then I'll just using that test and then tell people that it's okay, my type 1 error, my size of test is only about 4.8%. You just accept it, okay? That's what I mean is settle for that size alpha star test, okay? Which means that it's the largest possible error under null hypothesis. Over that, for example, you won't choose in that because it's actually larger than we want to be anticipated. We don't choose in that bigger than 5%. We are kind of very conservative, choosing something 4.8%. Okay. But if really picky, saying, well, I'm going to choosing some test, it's going to give me exactly 5% of type 1 error. What would you do? Actually, mathematical speaking, you should randomize it. That means whenever you reject it, your null hypothesis, the largest error you can make, which means type 1 error, is alpha star right here. It's 4.8%. Okay, the largest error you can make. Whenever you reject it, the largest error you can make is 4.8%. But whenever you don't reject it, in testing world, whenever you don't reject it, the only error you can make is type 2 error, but you don't control for it. Okay, hopefully understand what I'm saying. Okay, I'm saying it again because really critical point about testing it. So when we do testing, we always protecting alpha, protecting type 1 error. Okay, that's the reason why we are using alpha to find your critical region, kind of see it, right? Remember lambda x smaller than c. How do I find c? I'm using alpha to find c. Okay. During the discussion, we never talk about what your alternative space is, which means that it's frequentist conventional statisticians in doing this kind of testing, we always protecting type 1 error. Okay, so that means whenever you do not reject your type 1 error, only thing you can make error type 2 error, but you never control for it. You don't know what that is. So saying it's okay right now, if I don't reject it, if you still want to have in my size exactly the 5%, then you do what? You just toss your coin. Okay, you randomly generate your number. Okay, as long as your number generation, this guy's smaller than some cutoff, see right here. Then the C determined by what? How much space you have from 4.5% until okay. But so okay, this is 0.65%. Okay, so just trying to flip your coin, doing any randomizations, trying to fill out this gap right here. Okay, so by doing so, that will give you exactly 5% of the sizes of a test. Okay, to me, that it's really not necessary. I always go for 1. I'm more conservative. I'm more, trying to say, well, I don't want to make my error as large as 1, not just 5%. I always accepting that the test is smaller than 5%, but it's still manageable. As long as this guy right here is not really, really small. I always do 1, not 2. Okay. Good. So before I move on, anyone have any questions to see why when you do your discrete test, when your distribution is discrete, you may not necessarily find your cutoff that exactly give you a size alpha test. Okay, good. Then if there's no question, I'm going to move on to talk about what is the desired property of a test. I think that's really trivial. Okay, nobody want to make errors. So when we do testing, we always want what? We always want the error probability as small as possible. Intuitive. Okay, so I would say that a testing really, that's almost impossible. Almost impossible to do something. Almost impossible to do something you won't have any errors. But you do have this kind of trivial case right here. Okay, you do having kind of trivial cases, you won't make any error. But what is this trick? That's just something I talk about for fun. Okay, but in reality, you don't see that. And in this case, you don't even need statistics. Say if your x is Bernoulli, say that. Okay, keep in mind is your null space right here is not between 0 and 1. It's actually only what? Only 2 points, 0 or 1. Okay, that means you are doing an inference about a Bernoulli trial, but I say that could be only fail or success. The true theta is okay. Then if you are doing testing, saying that hey, my null hypothesis theta 0 versus the alternative theta is 1. Okay, if you do your decision making, if you do your critical region, say lambda is equal to x. So this guy right here is actually more easy to say it, more easy to find out it, but it's actually the same. So as long as I say observe 1, I call theta is 1. As long as I observe x is 0, I call theta is 0. Of course, it won't make any errors, right? So if you write this, okay, talking about if really theta is 0, if I do have my test region, it's x is 1, it's I rejected. Oh, okay. Right? Could you imagine why you don't make errors? Because underlying only theta 0, not going to be any successful, and theta is 1, it's always successful. As long as you observe 1, you call theta is 1. As long as you observe 0, you call theta is 0. You won't make any errors because theta only 0, 1. Okay. You want to do that, you could do that as well. Theta is 0, your Bernoulli trial. So 0, 1, then 1 minus 0, and then 1 right here. Okay, this guy becomes 0. Theta 1 minus theta minus 0. It's minus 1 is, sorry about that. 1 minus 1. This guy is 0. So that means you won't make any errors, right? If your theta is 1 right here, right? Oh, you reject null hypothesis. Right here. Okay, under alternate space, theta 1 minus theta, 1 minus theta, then 1 minus 1 is, right? This guy is what? Also 0. Okay, what does that mean? It's you are never making errors. Okay, whenever it's kind of trivial cases, okay? But well, it's just for fun. It's really not happening in real life, so forget about it. If you really know about theta only fail or success, well, you don't need statistician. You don't statistician. You know that by the person already, right? Okay. Good. So because we prefer some tests, the error probability as small as possible. So we do have some kind of rule to told you that it's what kind of test is actually optimal test. The optimal test means that it's some test is going to be what? To give me uniformly most powerful test. Again, uniformly is what? For over every state. For every state, the test is going to give me the most powerful test. Okay, but keep in mind, so-called label alpha tests. Okay, so that means we are going to choosing among the size of a test more than alpha, so-called label alpha test. Using that test, I'm going among in that big class, actually big is not small, among the class of label alpha tests, I'm going to find which one has the most power when we do like hypothesis testing. Okay, so again, it's I will fix type 1 error at alpha. Okay, at least not bigger than alpha. Then trying to minimize type 2 error uniformly. So that means I protecting alpha, but I'm going to using the UMP test, which will give me no longer what my theta is. My type 2 error areas is always bigger than other guys. That's so-called UMP test. Okay, good. Yeah. I know. So Chen Hao, right? Yeah. Yeah, yeah. 0 with power 0 is 1. I know. Jesus, I know that. But I mean, just taking a fun question right here. Okay, maybe I make error right here, but I forget about what right here. But what I'm trying to say is this guy is not making errors. Okay. Yeah, maybe 0 with 0 is 1, right? Making this 1 right here was more correct, right? If, yeah. Okay. If theta is actually 0, if theta actually is 1, you say x is 1, of course, probably should be 1, it's not 0. Okay. Thank you. Okay. Good. So, and then, so how do we find so-called UMP test then? So, I mean, in my class, after these lectures, you'll find one thing. It's, I hate to say so, but it's always like that way. It's, I hate to say so means that it's only thing in testing you need to do in my class is what you recognize a pattern. Okay, I had to say so means that it's in terms of mathematics, we always don't want to let a student know that it's as soon as you memorize a pattern, you solve a question without actually thinking about how to solve the question itself. Okay, but I just think it's easier for me to teach you guys in a more efficient way, that you really recognize a pattern and you would know what test you're going to use. Why should I say so? It's we do have so-called Lehman-Pearson lemma. Okay, this lemma from where? 1933. Don't blame me teach on something like almost 100 years ago. Okay, but Lehman-Pearson lemma we've been using so much, it's so powerful. Nobody actually replacing it in the new lemmas. So, but you will see what happens. Why is so easy to so powerful? Okay, so Lehman-Pearson lemma only apply to you have your null space is single versus, I'm not saying single, say simple. Simple versus simple. Okay. Again, I said pattern recognition. Okay. you're using Riemann-Pearson lemma to find UMP test only when your null hypothesis is simple versus simple. Okay, so right here it's if I do have simple versus simple, I use Riemann-Pearson lemma. Later on, I'll teach you that if I have simple versus alternative, what I'm going to use, then I will tell you what that is. And then alternative, or let me see. No, let me remember what I'm trying to say. Simple versus simple, simple versus alternative, yeah. And then alternative versus alternative. Then what will happen? I will let you know what will happen. Okay, but really is this kind of things I usually tell students you need to write in your cheat sheet for sure. But right now I don't have a cheat sheet, so forget about it. Okay, good, great. Then what does the Riemann-Pearson lemma told you that it's? How do we find UMP test? How do we show that it's the actual UMP test under this hypothesis testing? So now to imagine. So if I do have null hypothesis, theta 0, alternative is theta 1. Okay. Then the test region is about what? About ratio of two PDFs. Okay. Then the ratio of two PDF or ratio of two local function. One is given 1, theta 1, one is given theta 0. Okay. Could you imagine what is guy bigger making sense than some cutoff? Easy, right? Of course, we call this guy as a local function for a reason, isn't it? This guy nothing but local function. It's what does that mean by given theta? That means I supporting theta as evidence. Theta 1 more likely to happen if alternative hypothesis is actually true. Or in other words, if I want to reject a null hypothesis, I of course would say, hey, theta 1 is more likely to happen compared to theta 0. So that means as long as you're doing this kind of retesting things, if I given theta 1 more likely to happen, of course, that function could become bigger. So rejecting null hypothesis bigger than some kind of C. Okay, they do using a set region right here, then it's the other way around then. Okay, good. But of course, I want to make their size is alpha, right? That's type 1 error probability is size is alpha. So again, why? Let me give you something to think. It's easy. Because I always write this, right? I always write, hey, to need supremum theta in null space. This is what type 1 error should be. Then why I don't write supremum right here then? Why? Easy, right? Because your null space only have what? Single points. Okay? Hopefully don't find me so annoying, keep saying the same thing. You guys know that already. Okay. So I do want to mention that again and again. Because I do want you to keep good habits writing about alpha is supremum. Alpha actually is supremum over theta in null space. You need to write that every time. Okay, then think about what null space is. Okay, good. So why Riemann-Pearson lemma actually give you the most powerful test then? So say again, it's UMP level alpha test right here. To do that, okay, this would be the most powerful among level alpha tests. How do we show that? Remember this theory from 1933. So nowadays, well, almost 19 years old, right? Then you could see how easy the proof is. Okay, good. So say if I do have a level alpha test, delta star right here. Okay. We want to show that it's the power of the power of a test based on Riemann-Pearson lemma is going to be bigger than any other level alpha test beta star X. Okay. If we can show this, if we can show that, then basically you could tell people. Hold on a little bit. Okay. Basically, you can tell people the UMP test based on the Riemann-Pearson lemma is going to be more powerful, or at least not less powerful than any other level alpha test. That's okay to show so. Then it's actually easy to show that, as long as understanding why this inequality always holds. Why? Okay, here is why. So imagine if you having this kind of things. Okay, imagine if you have delta having 1 right here. So if you do observe, okay, if you decided to do delta is 1, if you decided to reject the null hypothesis based on Riemann-Pearson lemma, okay. So say if you another test theta start right here also equals to 1. If you have that means 1 minus 1, the first term become what? The first term becomes 0. Okay, so you don't have to you don't have to know what this is, right?
Sorry, we can't hear you. Dr. Lin, you mute yourself. We can't hear you.
Hi,
Hi,
you guys hear me now?
yes.
Okay, sounds good. Where am I then? So you guys see the screen? Yes, I see a screen as well. Up to where I lost you guys? Okay, let me see if I can go back to my slides. You guys see the slides right here, right?
Yes.
Okay. Up to where? You guys lost me.
I would say on the delta part on slide 19.
19. So, okay. Yeah, it's 1:45 right now. How about this? I will talk about it next time on Thursday. I'll repeat it. Okay,
it's fine.
so let's take a break, and then you guys coming back at 2 o'clock, but using the different link, linking to the 673 class. Then the range of midterm. Okay, of course. So the range of midterm number 2, good question. I never talk about it by writing a message. The midterm number 2 is going to be up to LRT. Okay, so as you can see in the midterm 2019 is a typical one. Give you something to working on the CILB and the UMBUE, and then end up with finding sub LRT. Is that clear? Okay, nobody answer me.
Yes.
Okay, got it. Thanks. Okay, thank you. Good. Okay, so apologize. I don't know what happens. You lost about 7 minutes ago. Okay, then I'm going to see whether or not recording will work or not. So I'm going to